Hi everyone. So in this video and the coming few videos, we discuss approximate second order methods. And basically the second order name in the for these methods comes from the fact that they depend not just on first order derivatives, which is given by the which are given by the gradients, but also in second order derivative information, which are given by the Hessian, right? And the second order gives you an idea of the curvature of the cost function in the local neighborhood of the current parameter setting, or of the point corresponding to the current parameter setting, right? So for example, if you have a line like this, the first order is positive in this direction, but the second order is 0, right? So here there is no curvature at all. Here there is curvature, right? Here there is even more curvature. Here there is less curvature, right? So the less the curvature is, the lower the value of the second order derivative. The higher the value of the second order derivative. So you can think of the Hessian as given this curvature information in all directions corresponding to the parameter space. Okay? So the method that we will discuss in this video is called Newton's method. And the idea is very simple. You are at the current parameter setting is given by theta 0. So you approximate the cost function by a quadratic approximation. So Taylor series up to the second term, okay? In the neighborhood around theta 0. So you approximate the cost function by a quadratic approximation around theta 0. If we do this, so let's call it j of theta, this is the approximation. It will be equal to j of theta 0 plus the first order term given by theta minus theta 0 multiplied by the gradient, plus the second order term which has a quadratic term in theta minus theta 0 times the Hessian, right? Now if I set the gradient of j of theta of this approximation equal to 0 and solve for the critical point where the gradient is 0, then I get this point right here, theta star equals theta 0 minus h inverse times the gradient. Okay, so basically what Newton's method does is that it approximates the cost function in the local neighborhood by a quadratic function, and then it jumps to the critical point. So it can be very, very advantageous, and that's the idea behind it, than solutions that depend on first order gradient, because it jumps directly to the critical point. Now, there are many problems with Newton's method, especially with deep learning, as we'll see. But one of the classical problems is that when you jump to a critical point, this critical point could be a minimum, but could also be a maximum, right? So it depends on the sign of the second order derivative, which is given by the sign of the eigenvalue of the Hessian in that direction. If the eigenvalue is positive, then you're going to a minimum. If the eigenvalue is negative, then you're going to a maximum, right? So instead of this, then it's like that. Now, typically with deep learning, as we discussed when discussing saddle points before, typically you have a large parameter space. Think of H as being a random matrix. It's more likely to have a mix of positive and negative eigenvalues than to have all the eigenvalues positive, or to have the H matrix being positive semi-definite. So if you have a mix, then you are likely going to a saddle point, right? So that could be a big problem, because then that kind of method can get stuck in saddle points. And to solve that issue, then there is a regularization technique where instead of H inverse, you add alpha times the identity matrix. And basically you are trying to push the slightly small in magnitude and negative in sign eigenvalues, you are trying to push them to be positive. Okay, now we'll come back to this regularization, but let's just say one more motivation about this Newton's method is that even if the function is convex and not quadratic, then this method, it will not reach the minimum in one step, but it will approach. So there is a theoretical proof that it will keep approaching the minimum. Okay, so even if it's not exactly quadratic, even though we are having a quadratic approximation, but it will keep approaching the minimum. Right? So Newton's method, the idea behind it is that you assume that at least in my local neighborhood of the point at which I'm in, that local neighborhood is convex, then I'm moving in the right direction and at a much higher speed than what I would do with stochastic gradient descent or any method that depends only on the first order derivative. Now the problem is that while gradient descent or stochastic gradient descent is likely to be repelled from a saddle point, right, because it navigates a trajectory rather than jumping to critical points, Newton's method will be attracted to saddle points. So that's why there is this regularization method. Now the problem with this regularization method is that if you take it to the extreme, if you increase the alpha by a lot, then you will end up doing a stochastic gradient descent, right? So the alpha I term will overwhelm the h term, and it's just you are going in the negative gradient direction, but you're dividing by a large value, which is the alpha, right? So it's as if, so it boils down, if you take that regularization method to the extreme, it boils down to stochastic gradient descent with very small step size. So it actually beats the purpose of the second order method, right? So this regularization method is useful only if it works with very small values of alpha. Now the second major problem with Newton's method, and that will motivate so both these two reasons, saddle points, which is a problem from an optimization perspective, and the other is a problem from a computation perspective, which is inverting the Hessian, right? So typically, if you have a number of parameters k, then the Hessian is a k by k matrix. To invert it, the computation scales with order k cube. So that can be very large. K is the number of parameters in the network, which is already a very large number. So k cube can be very, very large. So, so these two problems, optimization and computational, saddle points and inverting the Hessian, will motivate the other approximation or the other approximate second order methods that we will discuss in the coming videos. Thank you.